back to this course on polymer chemistry. In today's lecture, we will continue our discussion which we started on determination of polymer molecular weight, and today basically we will continue our discussion we had started on gel permeation chromatography or size exclusion chromatography, and then briefly discuss mass spectroscopy of polymers, in particularly MALDI top MS. Now, this is the last slide we had stopped in last lecture. Now, this is the typical GPC trace, where in the y axis you have detector response, and in x axis typically you have elution time, and which can easily be converted into elution volume. Now, if you want to convert elution time to elution volume, there should be the pump which are getting used in this GPC equipment should be pulse free, and it should be able to maintain the steady flow typically around 1 ml per minute. Now, from this raw data we must transform this data as a weight fraction molecular weight distribution, which is a plot of weight fraction versus molecular weight. The requirement for this type of transformation is this, because we know the definition of Mn is given by where W is the weight fraction of a molar mass chain, polymer chain having molar mass of Mi, and we can express this in terms of integral form like this. So, basically we need to plot this weight fraction distribution against molecular weight to integrate this, which will give us Mn. Similarly, Mw weight fraction, weight average molecular weight, can be obtained from the formula So, basically this is example of this is example of Mn and Mw expressed in integral form. This shows why we require the raw data to be transformed in this type of weight fraction molecular distribution with plot of weight fraction versus molecular weight. Now, to do that, let us first look at the principle of the separation in gel permeation chromatography. Remember, we have discussed that in the last lecture that you have in gel permeation chromatography, the polymers are passed through columns containing beads which have definite pores. So, when polymer samples is injected into this column, then the solvent takes away or carries these polymer molecules to the detector, and these pores which are in the columns which are responsible for the separation it brings about. Now, what happens? How the separation happens? The flow rate typically we work, the GPCs work like in the range of 1 ml per minute. It has been seen that the elution volume does not depend upon the flow rate, which means that the polymer samples are not carried away or dragged away by these solvent molecules. The polymer molecules basically equilibrate between the pores inside and outside, and the higher molecular bonds resides most of the time outside the pores, whereas the small molecular or small size polymer molecules they partition more inside the pore volume, thus taking longer time to elute. If we express this mathematically little bit and see what is happening. See, if we consider the elution volume V for a particular polymer sample as V 0 plus K E S C C into V I, where V 0 is the volume outside the pores, whereas V I is the total volume inside the pores, and KECC is the equilibrium constant, which basically is given by the concentration of the polymer sample inside divided by concentration of polymer sample outside the pores. So, for very large size polymer chains which has a larger size, it does not penetrate in the pore size. So, KSCC is 0. So, V is given by the outside volume, and if the polymer is low, the size is very low, very small size, then almost exclusively they will enter the pores, and KCC will be 1, which gives us V is V 0 plus V I. So, KSCC is basically the equilibrium constant between the concentration or the, because of the partition of polymer molecules inside the pores and the outside the pores. Now, from our thermodynamical knowledge, we can simply write that delta G 0 for pore penetration, Pp is for pore penetration, is given by RT ln this equilibrium constant, and del G can be written as del G is H 0 Pp enthalpy and T delta is 0 Pp. Now, as we know that in gel permeation chromatography, there is no interaction between the polymer molecules and the pores or the column. There is no interaction between them. So, del H, the value of del H for pore penetration must be 0. Hence, KSCC would be given by e to the power del S 0 Pp by R. Now, for a flexible chain, it can be statistically shown as this entropy for pore penetration given by this expression, where AAS is surface area of the pores per unit volume, and L dash is the mean molecular projection, which is basically equivalent to diameter for spherical polymer chain, spherical polymer chain, which is basically related to the size of the polymer. Now, as you can think that when a polymer molecule goes inside the pores, the conformational entropy of the polymer chain get reduced, because the conformations, the sum of the conformations which requires the central mass to be very closer to the walls, rigid walls of these pores are forbidden, which means the conformational entropy of the polymer molecules reduced or get decreased when a polymer molecule goes inside the pores, and this reduction of entropy becomes more prominent if you have large size polymer or if you have a small size pore. So, this entropy of pore penetration is always negative, and it becomes more negative if the polymer size grows or the pore size becomes smaller, and that is expressed by this expression, where if the pore size becomes smaller, AS goes up, hence the entropy becomes more negative. Similarly, if the polymer size goes up, this becomes higher and this entropy becomes lower. So, if we look at this expression here, and we know Kc is this and ESR is this. So, we can simply write from this to V is V 0 plus V I e to the power minus A S L dash by 2. So, this is the expression we can write, and which shows that V E decreases. From this expression you can clearly understand that V E decreases as decreases with logarithm of log of polymer size, log or L, hence polymer size. So, this expression gives us that, tells us that V E varies linearly, decreases linearly with the polymer size. As the polymer size goes up, V will go down. So, you can expect a linear relationship. So, if you plot log of size, polymer size, say if I write size against V, you expect that to be a linear graph. Now, from Mark-Hoying and Sakurada equation, we know that intrinsic viscosity is given by K m to the power A, where K and A are constant for a particular polymer solvent temperature combination. So, I can write log eta m is log K plus 1 plus A log m. Now, remember from our discussion in solution behavior of polymer molecules size, a polymer size, which is basically hydrodynamic volume. Polymer size in solutions means hydrodynamic volume VH proportional to eta m. We have seen this expression, these relations before. Hence, we can expect from this and this relation and whatever we have seen here, that log, as if the k and a remains constant, log m should linearly decrease with elution volume or VE. So, we expect that instead of log size, if we plot log of molecular weight, we can, or log of molecular weight, we can get a linear relationship between VE, where elution with the size log m goes up, VE decreases. Now, these two regions are the exclusion limit and this cutoff. They are the cutoff for the two regions where this is where the size goes up beyond this molecular weight, then none of the polymer chains can go in. So, they will have elution volume of V 0, and if polymer size becomes lower and lower and becomes such a low that all of them can penetrate equally in the pores, then all will come at the same time and this become V 0 plus V I. So, this is the region, linear region, where the polymers get separated. So, basically what in this, from this discussion we can understand that a plot of log m versus elution volume should give a linear relationship and V should decrease with increase in the log m. This is what is found in practice when we inject different molecular weight or sample in the GPC column. We do actually see that the elution volumes becomes decreases linearly with log m, and this has been taken advantage to make a calibration curve where known standard very monodispersed polymer samples which have very low polydispersity, like in this case 4 samples are shown here. So, they are injected and their elution volumes are recorded, and likewise a calibration curve is constructed by injecting many monodispersed polymer sample. So, we can, from this calibration curve, we can easily convert this elution volume to log molecular weight data. So, this is the way calibration is done for a GPC. Several monodispersed polymer sample with known molecular weights are injected in the column and their elution volumes are plotted against log of molecular weight, and such a linear plot is constructed. So, we can remember what the purpose. We were trying to convert the raw data, we were trying to convert this raw data to weight fraction distribution, okay, plotting weight fraction versus molecular weight. Now, from the calibration curve we can convert the elution volume to molecular weight. Now, what about the detection signal? Now, if for example, if you take a RI detector, then this output of this or the detection signal is proportional to the concentration. Typically, we use concentration detector. So, the output signal in this detector is proportional to the concentration, and if you assume that detector response is proportional to the concentration in the range we are working, and also this response does not depend on molecular weight, the output would be similar for a given concentration of different molecular weight. So, the output, if we assume that the output does not depend on the, it only depend on the concentration, not on the polymer molecular weight, then we can, this is the detector signal and this is the elution volume V. So, we can simply write the weight fraction dW of the polymer which eluted between V and V plus dV. We can consider the sample, this slice which is very infinitesimal slice. So, the weight fraction for the polymer which eluted between this V and V plus dV, we can write which is nothing but so this is, again let me repeat this, this is this dW is the fraction, weight fraction of the polymer chains which eluted between V and V plus dVW. So, this is the weight fraction for the polymer which eluted, and they can be written like this, where A is the area under this curve. And if we do integration n followed by normalization, we can get this weight fraction molecular weight distribution in the form So, this is mathematically we can do and show that this weight fraction distribution can be expressed by this formula, where this is the detector signal at V and this is the molecular weight which we got from the calibration curve for this particular V, and SV is the magnitude of the slope for this log m versus elution curve plot, okay, for that particular point V. Now, we do not have to do ourselves nowadays. Fortunately, softwares are available which can take this and give us this output of this type of output they can give, and from which, using the formula which we used at the beginning. So, now we can get the. So, these are the formulas for MW and MN we have seen in the beginning of this lecture. So, now we know what is Wm, how the weight fraction distribution varies with molecular weight. So, once we know that, use the help of the software, these things can be easily calculated. So, from the raw data, now we know that how from the raw data of a GPC trace we can get the distribution of number average distribution and weight average, number average molecular weight and weight average molecular weight, and we can also get the other MZ, and from the values of K and A we can get MV also. So, let us go back and talk about more about the calibration. Remember, we did calibration in, we have taken standard monodispersed standard. Monomer standard means very sharp molecular weight polymers, and then injected and recording their elution volume, and then for the calibration card we have plotted log m versus VE elution volume. There are few advantages, like this is a simple setup, only one detector is required, whether it is a refractive index detector or UV, we require one concentration detector, and solution we can do this calibration with without knowing exact concentration. Concentration can be variable little bit without no problem, and this calibration is very precise and repeatable. However, there are many disadvantages for this convention calibration. For example, if we go back and look at this formula, remember we said that as long as this K and A are constant, we can write log m instead of log size to construct this calibration curve. So, if the value of K and A changes, and that will change for a different polymer, even if we keep the solvent same and the temperature same, if we change the polymers, the value of K and A will change, value of K, and hence the intrinsic viscosity will change. So, we will get a different line, different curve for a new polymer, different polymers. So, this calibration curve between log m, log of molecular weight, and this elution volume is applicable only for a particular polymer, whose K and A are constant. Whenever we change K and A for a different polymer, obviously we get a new set of calibration. So, this calibration can be used to get a true molecular for weight of polymer. So, this calibration can be used only to get true molecular weights of the polymer which are same type used and calibration. So, if you have a, say for example, if you calibration is done for polystyrene, then using this calibration curve we can determine the molecular of polystyrene sample only, because the K and A value will remain same for polystyrene only. But if we, instead of polystyrene, if we change it to say polycarbonate, then K and A value will change. So, we cannot use this calibration curve, but Most of the times we use one set of calibration curve for lot of other polymers, which gives us error maybe 0 to 30% error in terms of molecular weight. The reason that we cannot get the calibration curve made for all the polymers, because we cannot get narrow disperse polymer for all types of polymers, especially for condensation polymers like polycarbonate, polyesters, polyamides. There is very difficult to synthesize narrow disperse polymer, which as PDI is 1.1 or less than that. It is very difficult, and unless we have a narrow disperse or monodisperse samples which can be treated as standard, we cannot use this for calibration. Hence, this calibration is mostly done with the polymers which can be synthesized with a precise monodisperse molecular weight, like leaving anionic polymerization. So, typically this polystyrene, polymethyl methacrylate, they are used as standards for organic solvents, organic soluble polymers, and the molecular weights are reported, the moleculars from other polymers are reported as relative to polystyrene or polymethyl methacrylate. And for aqueous soluble or water soluble polymers, the standards typically used are say polyethylene oxides, which also can be synthesized at very narrow or monodispersed standards. So, typically the water soluble monomers are reported in relative to polyethylene oxide standards. Second disadvantage is that if the polymers are different in branching, like different shapes like branching or other structural modification, we cannot also get that difference captured in the calibration. Let us go and go back and explain with the graphs. Like if you have different three polymers, as I explaining, for a given molecular weight, their sizes could be different depending upon the value of K and A or the intrinsic viscosity, and they can form a different calibration curve. So, if we use a calibration curve which is constructed for polymer A and use the same calibration curve for polymer B, then this error will be erratic. That is what we are explaining till now. This is the real example where several polymers are plotted, and you can see this each polymer has a different unique size, has a unique size to weight relationship. So, one cannot be used one calibration. If you use one calibration for the other polymer, there will be error. This is what we are talking about, the molecular shapes. Now, for a given molecular weight, see if you consider one molecular weight here and keep the molecular weight and change the shapes like from rod to coil to sphere, obviously sphere will have lowest size, then coil, then rod. So, obviously the elution volume will differ according to size. So, for a given molecular weight, if the size of the polymer changes, shape of the polymer changes, say like from rod to sphere to coil, then the molecular size changes and the elution volume is related to molecular size, not molecular weight. Hence, the elution volume also changes. So, this calibration, if it is done for linear polymer, we cannot use that for other shaped polymer like branch polymer, which will have different shape. So, there are two advantages we must remember using this calibration. Once that this is always reported with some relative to some known standards. So, there will be always some error, and linear polymer, if the calibration curve is done with linear polymers, if we find or if we determine molecular weights of other shapes using that calibration curve, there will be also error. So, what is done? To avoid this, remember we talked about again this that VH polymer size is proportional to intrinsic viscosity multiplied by molecular weight. So, if you can find out intrinsic viscosity of the polymer, then plot of log eta m and elution volume should, because this is now, this gives the polymer size and this is the elution volume. So, now this is independent of which polymer you are using, as long as we are using log of eta multiplied by molecular weight, that gives the size of the polymer, whether it is a different shape polymer or different type polymer. So, you get a universal calibration curve. So, if you can construct with one of the polymers, say polystyrene, then the molecular weight of the other polymer can be also determined using this calibration curve, as long as we know the intrinsic viscosity for the polymers we are using and the elution volume from our GPC graph. So, as long as we know the intrinsic viscosity of the polymers or the polymer sample we are using and the elution volume of the sample, using this universal calibration curve we can get the molecular weight, which is fairly accurate. Now, there are other detectors which can be used. Nowadays modern GPC equipment use like viscometer, which can detect the intrinsic viscosity online in real time, and light scattering detector, which can determine the weight average molecular weight online, which basically gives us the scope to find out this molecular weight distribution in actual sense. For example, if we have GPC with RI plus light scattering detector, then light scattering gives us the limiting excess Rayleigh ratio delta r theta is equal to 0, and if you are working a very dilute solution, we can consider concentration C is equal to 0. So, from these two we can real time we can get as the samples elute, we can get the molecular weight data in real time, and from RI detector, concentration detector, we can get the weight fraction automatically. So, we do not need a calibration curve if we have a absolute molecular weight detector like the light scattering detector. So, we can get a molecular distribution. Similarly, if we have RI plus viscosity, then viscosity real time gives the eta value, and then we can use this the universal calibration curve to find out the this molecular weight distribution. And if we have this triple detector RI plus, so GPC with triple detector RI plus viscosity plus LS light scattering. So, we get molecular weight, no standard required, we can get absolute molecular weight, and we also get information about shapes of the polymer, branching, etc. also can be obtained perform with this detector. These are the modern detectors available in the market. So, we can get. So, with this we come to discussion end of discussion on gel permeation chromatography. Okay, before that let us go through few practical points. For example, for organic solvents the beads are typically used as cross-linked polystyrene or surface treated silica gel, and for aqueous medium porous bits of cross-linked water soluble polymers are used. The resolution, the peak resolution is proportional to 1 over d square. So, basically if the bead size grows up, the resolution becomes inferior. So, it is always preferable to get a smaller bit size. For example, nowadays it is 5 micrometer or 10 micrometer at largest used, which actually help in get a better resolution. The resolution also depends on the length of the column, but not as much as the size diameter of the beads. It depends on length L to the power 1/2. So, if you increase the length of the column, the resolution goes up. So, preferably we use longer column. Typically in normal sense we actually use few columns in series, and some cases to make the process faster we the mixed bed type columns are used, where you have a different pores are the columns are made of beads with different pore size, and you can use 2 such or 3 such mixed bed columns in series, or a single or different pore size columns also in series. Obviously, as we have seen, this temperature plays more important. So, it is preferable that the column is kept in a constant temperature bath. Obviously, the sample loading is very small from a very dilute solution, especially when you are using detectors like light scattering and viscosity. There our assumption is the solution is very dilute, so that we can consider the specific viscosity divided by C as a intrinsic viscosity, and the molecular obtained by light scattering. So, there will be less error. High temperature GPCs are required for crystalline polymer. Crystalline polymers are not typically soluble in room temperature. So, they are actually used the molecular of them are they are dissolved at a high temperature, and the column is kept at a higher temperature, and the separation is performed at that higher temperature. So, we typically use this term high temperature GPC for that. And very high molecular weight polymers, typically more than 10 to the power 6 Dalton, they or 10 to the power 6 gram per mole type polymers might get degraded inside the columns because generation of high shear. So, we should be careful in using very high molecular weight in determining very high the molecular weight for very high molecular weight in GPC. And if you have complicated system like copolymers blend, we require more than one detector to fully characterize fully determine the molecular weight of those. Let us move to the next topic. Is this is the mass spectroscopy of polymers. Now, we know that in mass spectroscopy this which basically involves the study of mass of ions created by ionization or fragmentation and then determined electrically at the gas phase. For example, a molecule is vaporized and then ionized, and these ions are taken to the detector and the molecular weight is obtained. Now, while vaporization, the molecules may also get because it is a high temperature process, the molecules can get degraded also. But for small molecules which have all the molecules have same molecular weight, this fragmentation does not matter, because the highest molecular ion will represents the molecular or will give the molecular weight for the small molecule or the molecules. But in case of polymer, one polymer sample consists of many chains of different lengths or different molecular weight. So, if the polymer while vaporization gets fragmented or degraded, then while we get the molecular ion distribution, we do not know the distribution is because of the fragmentation or degradation of the high polymer chain or because of the actual presence of the low molecular weight chain in the sample. So, that becomes very complicated. So, if you are considering polymer sample, this fragmentation of the polymer chain during the vaporization is will give lot of error, and that is not acceptable. So, we must have some mechanism by which polymers can be vaporized without having any degradation or fragmentation of polymer chain. So, what is the modification done to get this the mass spectra of polymers? One soft ionization mechanism is used, where we will come in a minute, using matrix assisted laser desorption ionization or MALDI, by which the polymers are vaporized with help of a matrix without degradation. And we also use the second technique called time of flight mass spectroscopy, and in combination of these two techniques we get MALDI TOF MS matrix assisted laser desorption ionization time of flight mass spectroscopy, which is nowadays very important or very common for polymer samples. So, we will discuss a little bit of MALDI TOF now. Let us discuss the MALDI matrix assisted laser desorption ionization. In this case, a dilute solution of polymer sample is mixed with a concentrated matrix solution, and the typical the matrix typically of organic acids. And so, basically we make a dilute solution of polymer and then mix with a very concentrated solution of the matrix, which are typically organic acids, and a small alicate from this mixture is taken and applied to the mass spectroscopy plate, and it solidifies as the solvent vaporization. So, the small alicate is taken from the mixture and applied to the MALDI plate, and it solidifies as the solvent evaporates. The plate is placed in the source of mass spectrometer, and a short pulse of high energy, if this is a masked sample plate, and this is your sample along with the matrix, and a short pulse of high energy laser is irradiate the pellets, vaporizing the matrix. When as high energy lasers irradiates the sample along with the polymer sample along with the matrix gets vaporized, and in the vapor phase the polymer actually desorbs from the matrix. And if the polymer is ionized, already a charged polymer, this is fine. If it is not charged, it is a neutral polymer, then we have to add some salt to cationize these polymers, so that they can move towards the detector. So, the neutral polymers are ionized or cationized by protons or metal cations like sodium Na plus, K plus or silver plus. So, this is the name, as the name suggests, we need a matrix assistance, we take assistance of a matrix to vaporize by help of a laser radiation, and in the vaporized states the polymer gets dissolved from the matrix and then ionized and then get ionized. So, this name MALDI comes from there. So, in MALDI, the matrix, choosing of matrix is very critical, and it needs to be optimized for every polymer samples. It must form uniform solutions with the polymers and the added salt. It must strongly absorb the laser wavelength, so that the ionization the can be taken place, vaporization can be taken place, and it should give rapid vaporization. The salt, we said that neutral polymers need assistance from the salt to become cationized, and for example, this polyesters, polyamide, polyethers who has a heteroatom, salts like sodium, potassium and lithiums are used, because these salts, these cations, sodium, potassium, or these alkali metal cations can attach with this heteroatom and cationize this polymer. The polymers having unsaturations, the silver cation can be used it can actually complex with the pi bond. For example, polystyrene, polybutadiene, they can, for this polymer silver cation can be used. For olefinic polymers like polyethylene, polypropylene, it is very difficult to find a cation which might complex with this olefinic polymer. So, it is very difficult to cationize and analyze these polymers by MALDI. And low solubility polymers which does not soluble in a solvent is also very difficult. The solvents must be chosen such that it should uniformly if you evaporate quickly to give a uniform mixture of the polymer, matrix and the salt, should quickly evaporate and give the matrix and salt. Let us talk about the mass analyzer, time of flight mass analyzer, which is basically a source. This is the source for the mass spectrometry source, where the matrix is vaporized and polymers are ionized, and then they are taken to the detector. And in this case, the case of time of flight mass analyzer, it is the every cations are they actually travel same path. All the molecular ions follow exactly the same path to the detector, and the only the detector measure the time which the ions take to reach the detector. The smaller, the heavier ions would take more time to reach detector, where lighter ions obviously will take lower time and move faster to the detector. So, this is example of one MALDI from PMMA, polymethyl methacrylate, and you can see these are the peaks from different polymer chains. So, this gives the entire distribution. This is the normalized intensity, and if you look at the gaps between the molecular ions, you can see the gaps is 100 Dalton, which is exactly the mass for a MMA repeating unit. Okay. So, here you can exactly get the difference in the signals with the molecular weight of the repeat unit, and from this distribution the molecular weight, different molecular weight like number average molecular weight, weight average molecular weight and other molecular weights can be directly obtained. So, this is absolute technique, no calibration is required. Quickly go through advantage of MALDI-TOF. It is a small amount of samples required, very sub-milligram sample require, and this analysis happens in fast, very within few minutes compared to the other techniques, is very efficient. It does not depend whether the polymer structure is a linear structure. For example, for gel permeation chromatography, we typically use the principles and postulates of a Gaussian flexible polymer chain, but in this case you do not need any polymers having any shapes or any structure can be determined, and the MALDI works very efficiently for low molecular regions where GPC does not work, and others other information besides molecular weight averages and the polydispersity index, the repeat unit mass, N group mass, these are also can be received. So, just all these benefits, but the only disadvantage is that the price of MALDI-TOF is very high. So, it is not very convenient to use MALDI-TOF in every lab. So, with this we stop the discussion of determination of molecular weight, and we will move to the next topic in next lecture.